Hi everybody. Today we will talk a little bit about the new AC mains line dimmer, the MPDM version 4 that was just released about a week ago, and we will try to see how easy or complicated it's to use it with an ESP8266 board. In this case, again, we will use the next evolution board, but uh, as you can see maybe from the previous article, this dimmer driver, it's an universal one, so basically you can use it with your Arduino, with your STM, with your ESP, with your whatever microcontroller are you using these days. It's very simple to interface because you have on the driver absolutely everything that you need. So the only thing that you need to provide is a voltage. It has a voltage control pin, yeah. So basically just bring to this pin, to the command pin, the voltage from, let's say, 0 to 2.8 or 3 volt, or depends how it's calibrated, and that's it. So basically you don't need to do any more intensive consumption calculations on your microcontroller. You don't need to do any kind of zero crossing detection. You don't need to do any kind of phase control. Just provide the step voltage for the command, and that's it. So a very short and brief presentation to see what we have here. So basically we have the mains input output stage here, yeah. This is the mains input, yeah. You can see live and neutral, and we have the output to the light bulb, and on the input we have a proper fuse, a proper MOV for protection. We have the triac driver, and on the downside, or on the right side, as you can see it on the screen, we have the fully isolated phase control detection channel and the fully isolated triac control channel, yeah. As you can see from the PCB, the command part of the driver, it's fully isolated, and you can see also here an extra isolation slot, so it's no contact between the mains and the command and control stage. To the input we have also our phase detection circuit and driver, and the PWM generated on board. Now let's see a little bit about sorry, let's see a little bit about the signals that we want to take a look. So these are the signals that we are interested in to see today. In purple we have the output of the phase control. In blue it's the command input voltage, yeah. This is, if you want, the output of the ESP board. On board you will see later we have a DAC, but you can use also PWM or whatever. I'm not using PWM in case of ESP8266 because, as probably most of you knows already, ESP8266 doesn't have a proper PWM inside. It's not hardware, it's a software PWM, and that means again using CPU power just to generate the PWM signal. And basically the idea was to just get rid of everything from the ESP8266 and to use it as a proper application processor, if you want, application MCU, and all the function that we need, for example, for dimming or for motion control or other things, to just go out on the dedicated drivers. And the yellow signal, it's actually the output from the driver, and this one, as you will see later, it's fully PWM signal. Now maybe you can see it's duty cycle 95%. We have the light off. Let me try to show you a little bit better in here. So this is the purple signal that I said it's the phase control. Yeah, so this is coming from the phase detection unit, and the phase detector output, it's actually right here. Yeah, so you can see the probe there. This is the purple channel. Yeah, it's connected there. The blue signal is coming from the first channel of the DAC. Yeah, so it's just here. Here we have the 4 DAC channels. On the next evolution board, I have on top the AN1, the analog extension board, where, as you know already, we have a DAC with 4 channels. Yeah, it's an MCP4728. Yeah, so yeah, probably you are thinking already that it will be very easy to hook up 4 dimmer drivers and just to have 4 full AC mains channels that can be dimmed. Yeah, and it will be no overhead on the ESP8266. Yeah, basically this is the idea with this driver, as I said before. Yeah, so this one, it's the command voltage, and you can see it here in blue. Yeah, it's this blue signal. We have right now 1 volt per division, so we have 2.8 volts. Yeah, it's there almost 3, so it's 2.8. This is calibrated now to run from 0 to 2.8 volts. So basically at this 2.8 volt, the light, the bulb, it's off. Yeah, the duty cycle here, it's 95%. Yeah, and the yellow, that it's the output signal, it's hooked up here. Yeah, so it's coming just out of the output of the PWM driver, and it's going to the mock that is driving the triac. Yeah. Another thing that I want to tell you about this driver implementation, just for, let's say, safety and make it easy to be packed in a box, even a metal box. The triac that we are using, it's actually an isolated one, so basically you can touch it without killing you. Yeah, so this is a triac that has the tab isolated. Mostly of them are not, so you need to be very carefully. As a good practice, don't touch it. It's better to not touch it. Yeah. Okay. Yeah, so this is how is looking our setup for today, and now let's go a little bit to the software side. I know everybody's looking forward to see what's happening from the software point of view. So what do we have here? It's a very simple implementation of software driver for the MPDM version 4 dimmer. Yeah? So basically what we have it's the driver for the MCP4728. Yeah. This one is already saved. As you can see here, I saved it already on the ESP, and to use it, it's very simple. So basically what we need to do, it's just to set the ID of our I2C bus. We need to set up our SDA and SCL channels. In our case they are 2 and 1. We need to set up the DAC address for MCP4728 that we have on this AN1 board. It's 060 hexa. We need to choose the channel that we want to use to command the driver. In our case, as I said, we will use channel A. So channel A, it's 58 hexa. Yeah. And another important thing that we need to set up before using the driver is to establish our voltage reference or voltage calibration. MCP4728 can run in two different modes. In this case, I choose to use the external voltage reference, and actually this external voltage reference, it's now basically the VCC. So just go and measure your VCC and put it down here. In my case, it's 3.2325 volts. To use it, it's deadly simple. Just call the MCP4728 driver module, initialize your I2C bus, and write your voltage command voltage. The entire process is, if you want, just set and forget process. So in your application you can just go set the DAC channel value, actually set the channel that you want to choose, set the value of the voltage command for that specific channel, and that's it, end of story. If you want the participation in the process of your application processor, or in this case of the ACP, the ESP8266, it's ending. The driver will run itself and will keep it running very smoothly. Yeah. So let's give it a try. Let me restart. Let's also see on the oscilloscope and on the live board what's happening. We will initialize the main variables. We will initialize the I2C bus, and let's set also the command voltage. As I said, 2.8 is the maximum voltage as it's calibrated now. That means here having a duty cycle of about 95-96%. Yeah. And here you can see the signal with the corresponding duty. You can see the voltage at 2.8, 2.9 volts. You can see it here. Yeah. Yeah. And the stable output from the phase detector circuit. Yeah. So as you can see, for the phase detection we have a period of 10 milliseconds and a frequency of 100 Hz, and it's normal because we are using here 240 volts 50 hertz. We are in Europe. Okay, so let's see on staging what's happening and how the driver is reacting to the different voltage commands. Yeah, so as I said, 2.8 volt. This one is if you want let's say 95% duty cycle, and this is corresponding to the lowest light, let's say lowest light. Yeah, if we are going down, for example the next one, 2.7, we can see that the duty cycle is changing. We are at 86%. You can see here also the waveform is changing. Yeah, and the command value usually is coming down. Yeah, and if you are looking to the bulb, you will see that it starts glowing. It's glowing very dull, but it's glowing there. Yeah, you can see it's very stable. This is something that you cannot obtain with ESP8266. Driving it directly, and to try to do, for example, your phase control and zero crossing detection in software in the ESP module, and for example run also properly a web page. There are also problems related with the interrupt and other things. ESP8266 doesn't work very well when you want to use real-time two interrupts, for example. Okay, so let's increase it a little bit more. Now you are able to see it properly increasing the light. On the driver, duty cycle now it's 78%. You can see also the wave form changing and the voltage command value decreasing. Phase control will stay all the time, obviously at 10 milliseconds 100 hertz, because this is the 50 hertz signal that is coming from the mains line, and it's used for the phase detector. Okay, 2.5, 72% is changing. 2.25, 2. Now you can see we are about 47%, almost 50% duty cycle. You can see now very well on the waveform this almost 50% duty cycle, and the voltage has come down. You can see we have 1 volt per division, 2 volts. Yeah, and let's go down and down and make it brighter and brighter. One to 5, 1. At 1 volt, you see 1 volt per division. At 1 volt, we are already with the duty cycle at about 18-19%, and you can see the waveform. 0.75, 0.5. At 0.5 volts, we are about 9-10% duty cycle, and if we are going to 0, then duty cycle it's actually about 2-3%, but now it's just jumping around. As a good practice, I think you can keep, let's say, the values between, I don't know, 0.2, 0.3 to up to 2.8. Yeah, so maybe with a 0.25 here we can see it a little bit more stable. Yeah, so we have a duty cycle of 8% at 0.25. Yeah. So it's reacting very quick, very well. It's very hard to see now because of the camera autofocus, what's happening in terms of the light bulb. Actually, this driver has also let's say inrush current limitation. So basically, when you set the voltage command from let's say lowest light to the highest light, so you are going from 2.8 to 0, it will not give directly the zero voltage, so it will have a little bit of stepping just to avoid the maximum inrush current going through the light bulb. Yeah, so basically when I'm setting now 0.5, it will have a stepping. It's impossible to see it because of the autofocus and auto exposure of the camera. Okay, so actually you can see it, and some people told me to show a little bit more when it's at a very low light stage, because this is the stage where usually the traditional drivers are badly flickering. So as you can see here, the light bulb filament, it's very dim. Yeah, it's very dim, but it's stable. Yeah, and it's normal to be stable. You need to keep in mind that we are using here a DAC with 12 bits resolution. So I've used a similar driver many years ago for let's say setting up lights on lux level precision. So basically it was connected with lux meter, and you know, the light was set it up like, you know, 300 lux precisely, or 200 lux precisely, or whatever value was necessary. Okay, so this is how it's looking in terms of basic functions, and I will show you also how quick and easy will go, let's say, through dim phase without charging too much the application MCU. So I've just defined a timer. I just defined a timer here. So basically every 1 second it will increase the voltage command value with 100 millivolt, and when the voltage command will reach the 2.8 volt, then it will be set up to 0 and the process will restart. Yeah, so let's see how it's working. So let's try to keep an eye on the oscilloscope first. You can see now very clear how the duty cycle of the PWM driver is changing, and how the voltage command value is increasing. You see it's starting from 0 and is going up. The PWM duty cycle is changing dynamically, and also you can see the light changing. Okay, so that's all for today. Thank you for watching, and if you like it, please give me a big thumbs up, and see you next time. Bye bye.